Oh, I forgot my image. All right, let's just get situated here. Charge my laptop. All right. Just turn off the music. All right, so this will be the fourth stream. We're starting to get into more and more speculative territory here. This is stuff I've done a lot of calculations on, essentially, but I don't really have any like complete proofs. I have a lot of the smaller vertex examples that I've computed, and everything there sort of makes sense with our intuition. Me and Professor Baranovsky, that a lot of this work I did with. So yeah, I wanted to mainly compare essentially three different ways of looking at the same problem. So this is like what you might think of like as the original way of viewing the problem, where we're not really including any operatic information. We're just doing the various maps that we have from the graph homology stuff. So we had delta maps, which copied Simplices. We had this Xi homotopy, right, which was the homotopy that fixed the map where we have the chains on some Cartesian product power, and then we can split it into tensor products. Right, there's this AW map, and there's also this EML map backwards, right? And the composition this way is not the identity, but it's homotopic to the identity, and this H is the Xi homotopy, which sort of corrects for this lack of the fact that this composition is not the identity. Hello, chatter. Yeah, so anybody that's just coming in, we're just sort of reviewing the research stuff I was talking about the last few streams. We have this graph homology stuff. All the maps are composed of these delta maps on Cartesian products. Some composition of these deltas, Xi homotopies, which I was just explaining here. And then also the AW map, which is right here, just explained. So these are our main tools, or I'll call them tools, but really they're just like the maps that make up what's going on in this picture. But we have a sort of isomorphic, or maybe it's quasi-isomorphic, I'm not really 100% sure here, picture in the setting here. So instead of viewing everything as simplices in this Cartesian product, we can kind of leave the simplex in M alone here and sort of view everything that's going on in here with these maps. There's analogous maps for these other types of objects, which are somehow like keeping track of what's going on here in an operatic sense. And actually, so my conjecture, or this isn't proven, but I believe that everything that you get from composing these maps over here will be like quasi-isomorphic or isomorphic to some composition of maps here. I'll just write it like this, just to be a little informal for a second. Actually, let me this will make it a little. more coherent, I think. So yeah, let's just compare the three maps here that arise in this setting, and then the analogous maps over here are there's a delta for the BE elements, where instead of delta operating and creating new new Cartesian products, what it's doing here is it's just creating like a new like element in the partition, essentially. Like if I take a upgraded BE element such as like 1, 2, comma 3, and I apply some like delta 1, 4 to this or something, that just means I'm copying the 1 position to the 4. So I'm essentially creating a 4th element and I'm adding it to the partition that includes 1. So 1, 2 becomes 1, 2, 4. And then 3 just stays the same because that one wasn't affected by the delta. So yeah, just essentially the delta, ij would just be, I look for where the partition that includes I is, and then I create a new j element, and if there's any numbers that are higher than j, I need to like renumber them. But in this case they weren't, because 4 is bigger than all of the other numbers. But I could also have like a delta 1, 3 here, and then this would become 1, 2, 3, and then 3 would shift up to becoming 4. Okay, so essentially there's deltas here, little h and AW, and on the operatic side you have similar types of maps, except now they operate on these types of things instead of simplices in the Cartesian product of these m's. So yeah, if you weren't following the other 3 research talks, then you might be a little lost at this point. But to sort of summarize it, what's going on, you have a picture in this Cartesian product. I've sort of come up with a way that like keeps track of what's going on here, but just by using the numbers essentially. Yeah, because there's a lot of extra stuff, kind of like superfluous information in the, like if you write out what these maps actually are. The compositions of these, I mean. So yeah, I've sort of like, in some sense, like streamlined the data and, just using numbers now and, tuples of numbers, right? Or essentially tuples of permutations, but sometimes the permutations are themselves permutations of partitions. They might not be like, yeah, you can see, like we partitioned possibly they're partitioned, but the partitions could also just be, singletons, like 1, 2, 3, whatever. Right. So what do we have over here? We have delta maps. On the operator side, we have like a similar map, which I'll call like the operator she, or here I'll write a TC because, or actually TR, just to differentiate it from something I'll talk about probably later. But yeah, in this situation, there's also a similar thing, but this is just I'll just write this as like H phi or something. It's a different H map. And then instead of AW on the operator side, we have this composition where I can like detuple something with this phi map. So instead of viewing things as like a permutation of partitions, I can just view it as a normal permutation, like 1, 2, 3, or 1, 2, 4, 3. So that's what this phi map does. And then after I view it as a normal permutation or a tuple of normal permutations, I can take the table reduction map. And if I do that, that corresponds to the same thing that happens over here when I take AW. But of course, it's like the action of this, because here we're going to get surjections. Here we're going to get some, tensor product of things in M, but that's going to be the action of those surjections. And we talked about, I think, 1 or 2 talks, maybe it was research talk 2. If I'd have some surjection operad, or an element from the surjection operad, we said how does it act, and it gives you a tensor product of simplices. Right, let me just slow down for a second and catch my breath. Right. So anybody that's, I'm definitely looking for anyone out there that's, involved in this type of mathematics that maybe could help me. Um, as well as anybody that just, has good questions or, yeah. So yeah, does anybody have questions? And then here, yeah, it's very similar, just table reduction phi. But these H maps are a little bit different. So here there's a Xi map, which is correcting here, and these H maps, I've kind of invented these myself. So these are kind of speculative. This H has been well established. This kind of gives, this quasi-isomorphism is well understood. Because there's algebraic topology proof that, essentially the Cartesian product and the tensor products have the same homology. And so there's this, old story about that stuff. Right. What else do I want to say? So any questions in the chat? If anyone's still following along and brave. You could also throw in rotations in here, but the rotations actually don't show up in the graph homology stuff. So there's rotations of, you can permute the elements here. You can also permute like the numbers in the permutations here, and yeah, same thing with this other story I'll talk about in a second. But all right, I don't see anything in chat, so that's either really good or really bad. Either nobody's in chat at all, or no, I'm just kidding. Right, so it basically just, I think the proof is going to boil down to basically an argument that whatever we get in this picture, it can be translated into this picture and also translated into this picture. And when I take AW at the end, if I want to know what the result is, it'll be some action of some surjections that you'll get from either of these processes. And we'll have to prove, or it'll be a nice proof to show that what you get from both of these is the same answer. Yeah, so let me see. Right, so maybe I should just do an example where we show, so in here we're going to get joins of simplices in this Cartesian product. And like I was saying, there's either an I'm not sure yet how I should state it, but I think they're just isomorphic as simplices, but there's certain joins of simplices in here, and then I can just take sigma tensor whatever I get as the result of this, and it should be a theorem that those are isomorphic as simplicial sets. And then there'll be another statement for this setting, but I don't think this one will be exactly isomorphic. It'll be like quasi-isomorphic to this one, and then, yeah. So there's going to be basically two sort of statements. We're going to show whatever happens in this picture is the same thing that happens here, and whatever happens here is the same thing that happens in the original picture. And the thing that's important here is that all of this stuff gives us like a way to compute this, which is kind of like a naive way of looking at it, where where you don't have anything to like, where it's like naive, like you haven't computed the actual surjections that you can represent the action as, or the coaction, whatever. All right, so yeah, probably if I don't go to an example, it's going to be increasingly more and more confusing. So let me think. Let me do a quick example. Let's not talk about this yet. Let me just do the first two. No questions? Okay. Or yeah, let me just spell out a little bit more about what these two things are actually. Okay, so the types of like sums of simplices, or yeah, the types of sums you're going to get from the graph homology stuff in this, C star of the Cartesian product. All right, so one of our examples, I think maybe we looked at a couple times ago, was we had the map coming from collapsing a graph like this, where it has 1, 2, 3. So we're going to have a delta 1, 2 and a delta 1, 3. It just depends on the ordering. So there's two different orders of collapse. You could have delta 1, 2, H, delta 1, 3, AW. So remember I said these are our main tools: delta maps, Xi homotopy, delta map, AW, right? So nothing new from what I just wrote, what I just erased before. And this corresponds to collapsing 1 into 3 first and then 2 into 1, because you kind of have to view it backwards, which is a little bit confusing, but this delta 1, 3 on the left here means that 1, 3 collapsed first, and then we collapse 2 into 1 after. And because this is like sort of out of order, that's why we would expect this map to be non-trivial. If we do it the other way, where it's like delta 1, 2, delta 1, 2, then it will be in order, like 2 collapses into 1 first, then 3 into the result, and that is sort of like in order, and we would expect that not to give anything interesting, because there's basically nothing that needs to be corrected in that case. But when we collapse things in the wrong order, then there is an error term essentially that needs to be corrected for. Because 3 into 1 is not equal. 3 into 1 first, then 2 into 1 is not equal to 2 into 1 first, and then 3 into 1, if it's a non-commutative algebra. So yeah, what's happening here? So we're plugging in sigma into here. So here we're not talking about any operator stuff just yet. I think we got kind of to this point, I think, at one part. Maybe another time, but so h of sigma comma sigma, right? We duplicated 1 to 2, so now we just have two copies of sigma. So what is h of sigma comma sigma? So I thought of maybe a better notation for this. So this is going to be a sum. This is going to be a sum. And remember, we're going to create these overlapping partitions. And in this case, just because of the definition of Xi, there's going to be 3 overlapping partitions. The first one is going to be basically duplicated. So it's going to be delta 1, 2 of sigma A1. And then I'll use this as a symbol for join. So this is just a join. A join of simplices just means, like, if I have sigma 0, 1 and I join it with sigma 2, 3, then I just get sigma 0, 1, 2, 3. All right, so joining simplices is basically just like you're concatenating the vertices. So here I'm just taking the first overlapping partition, I'm duplicating it into the first and second position, and then I'm joining that with the result of applying AW to basically the right half. So I get an A3 here, sigma A3. Or actually I get an EML of sigma of A2 tensor product with sigma of A3, which is basically the result of AW of the second half, second piece. So we apply AW to we basically do nothing to the first piece, so we get an A1 here still, and then we apply AW to the second piece, and it breaks it into A2 and A3, and then we apply EML to go back into the Cartesian product. Right. So then what does delta 1, 3 do here? Well, it just duplicates another one of these, so we get delta 1, 2, 3, or maybe I'll just write it as like delta superscript 3. But this is, so it's going to be AW of, and so same thing. And forget about the negative sign for now, but it depends on the overlapping partition, of course. Where was I? Oh yeah, -1. Yeah, so this becomes like a triple delta sigma of A1 join yeah, and then delta 1, 3 how do I want to say this? Yeah, so here this is EML of delta 1 to 3, so that applies to the first one. Yeah. Okay, now I'm getting a little confused. Does the delta go on the inside or the outside? That's probably important. Yeah, maybe it needs to be on the outside. You apply EML. Yeah, you're gonna apply EML to 2 of them, and then duplicate on the outside, I think. So EML sigma of A2, tensor sigma A3, and then it's just going to be, yeah. Okay, I think that's right. Oops. All right, so yeah, as you can see, even just this small number of compositions, trying to write it out this way, even in this like simplified notation, is still getting very annoying. Like I'm already confused on whether the delta should be like on the inside or the outside of the EML map. I think this is right though. Yeah. Yeah, that should be fine. I think that's right. Yeah, so the question is like, what do you get when you take the Alexander-Whitney map of this like giant mess? So you have a join in here of stuff, like you have all these different deltas. Yeah, and then let me just for completeness, let me write this another like in the other notation I was using the other day. So this is like similar to saying like this is the AW of, we have 3 A1s, so it's like A1, 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 just meaning that all these components are the same essentially for the first, second, and third Cartesian factor. Then the second, then it's joined with, now we have A2 and A3, but the A2 and A3, the A2 has been copied to the third position. So it's like A1, A2, A2, and then A3. And I'm writing it sort of like in this way because where there's a blank space here, this is all like, when you apply the EML map, you get a bunch of degeneracies. So there's essentially, wherever there's A2 terms, there's degeneracies here. Wherever there's A3 terms, there's going to be like degeneracies over here. But they kind of get shuffled amongst themselves if you look at the definition of the EML map. So sometimes the A2 terms will be over here. Sometimes they'll be over here, and the degeneracies kind of, you got to look at all possible shuffles, essentially. But I'll just draw it like this for now. Right, so essentially, yeah, 2 different ways of looking at the same thing. And this join here is like joining this stuff together. And these are, you're viewing this as like sigma of, and then the numbers that make up A1, sigma, the numbers that make up A1, sigma, the numbers that make up A1, and those are the three Cartesian factors. So this is sigma of A1, A2, and then some number of degeneracies here. This is sigma of A1 joined with A3, and then some number of degeneracies here, and then A1 joined with A2, some number of degeneracies. And of course, yeah, I mean, this is like a sum over these terms, right? Sum over all the A1, A2, A3. Okay, right. So the question is, how do we take the AW of this? It looks kind of complicated, and I think that's why this problem is a little bit annoying. So yeah, I mean, here's where the formula would come in. I mean, you'd like to just say that this is just the some surjection action, but then it's like which action is it, right? And that's where the viewing it in the other way comes in handy. When we view it the other way, we can just say, oh, we have these elements, I can just take a table reduction of them, I get a bunch of surjections, and it's our job to prove that those are the correct surjections that you get from taking the Alexander-Whitney map of this thing. Right. So let's just, maybe I'll try to say how we would speculate what the AW of this is, but let me just say, just looking at it, it's not very easy to just see what the AW of this is, but we'd like to say that it's the coaction of some surjections right, but which ones? Hello. Yeah, no problem if you're late. You'll probably be a little bit confused if you missed the other ones, but essentially we're looking at graph homology terms, and the terms that we get from graph homology are very complicated like this, where we have to take this Alexander-Whitney map of like a sum over a lot of different terms, and they all have this type of form, where A1, A2, and A3 are overlapping partitions of sigma 0 through n. You have some n simplex. So yeah, taking the Alexander-Whitney, you can sort of, for this one, you can sort of kind of deduce what it is by using a little bit of reasoning. You know where the degeneracies are, so what, when you take the Alexander-Whitney map, if you include one of the degeneracies, then we're dealing with normalized chains, so you'll just get nothing. But it would be nice if we could just do all the math on like the operatic side and then take a table reduction map at the end and hope that when we take AW of this stuff, it should be the same thing as the coaction of all the surjections that we get. So yeah, I mean, you can sort of go through this and kind of reason that like, okay, A1 and A2 are next to each other. So if I'm taking an Alexander-Whitney map and I include A1 and A2 in the first piece, well, they're an overlapping partition, so I'll be including the same vertice next to each other, and that means it'll be degenerate. So you can sort of deduce that, okay, it has to go through just one piece of A1, but it has to stop before A2, and then I break the second piece of A1 in the second component, and then I go past the join, and I include all of A3 here. So these degeneracies actually have to be on the other side, or else I'll be getting 0 in the normalized chains. And then finally, that just means that all of A2 has to be included in the third part. And so actually you can show that it's not easy to show this like directly, but you can show that the Alexander-Whitney map of this is going to be the coaction of 1, 2, 3, 2. So it's 1, 2, 3, 2, applied to sigma, we'll say. Or acting on, the coaction of 1, 2, 3, 2 on sigma. but yeah, like where does this 1, 2, 3, 2 come from? It's the table reduction of something, but like how do we get, how do we construct this calculus to be able to say, okay, this is the BE element, and then I can take a table reduction of it, and hopefully I'll get 1, 2, 3, 2. And so the stuff that I've come up with is that essentially, okay, we have this delta H, delta AW stuff going on here. I've come up with analogous maps that just deal on the operatic side and essentially keep track of the same exact stuff. So there's an analogous delta, like we just wrote down on the last board. There's a capital H, which is analogous to the little h, she. Yeah, so all the deltas can be reproduced on the operatic side. The h's can be converted into operatic she, and then instead of AW, we have a table reduction, which is sort of replacing AW in some sense. Table reduction, and then yeah. Okay. And actually, when we go back into the Cartesian product, there's also this story with the table completion, but it's a little bit confusing, so I don't want to jump into the table reduction, table completion stuff exactly just yet. No, that's okay. Yeah, I mean, I don't expect everyone to know that. I mean, it shouldn't really be familiar to anybody except, people that study this. So, but I mean, if you want to learn the stuff that's the basis of this, this is basically algebraic topology stuff. So we're dealing in simplicial sets, trying to study, it's a way of viewing like how you can build up different shapes, different spaces from essentially triangles of different dimensions. So you have like regular 2-dimensional triangles, you have tetrahedrons or 3-dimensional, 4-dimensional, and you can kind of build these spaces up. But yeah, so yeah, trying to do this all on the chains on the Cartesian product and not introducing any operatic stuff or table reduction is quite annoying in my opinion. You have like a crazy amount of terms here. And if you don't get rid of the degeneracies, there's like even more terms, but they're obviously 0 in the normalized chains. And so yeah, it's just a big mess. You're trying to take the Alexander-Whitney map of all this stuff, but it's not exactly clear what you should get in the end. I mean, we have to prove that we should be getting some sort of surjections operations, but yeah, it's just not very clear. I mean, that's the whole point of this essentially, is making this more clear. But yeah, so instead of doing this, so this is the hard way. Now let's compare it to the operatic way of doing it, and let's try to get the same answer here, right? So 1, 2, 3, 2, and again, that's just because if I take the Alexander-Whitney map, I'm going to be getting tensor products in the end. I'm going to be getting A1 in the first position, so it'll be like sigma, it'll be some sum, sigma A1, tensor, sigma A2, A4, because A1 became A1, A2, so this A3 became A4, and then tensor, this A2 became A3, and that's how we got 1, 2, 3, 2, because this is the coaction of 1, 2, 3, 2, acting on sigma. Okay, and we did that another time where we talked about if you have surjections in the surjection operad, they can act on simplices in C star of M, and they have a coaction. They create these sums of these tensor product things, which are, they're you can think of them as actually, I believe you can think of them geometrically as like prisms. So they're like prisms in the Cartesian product. And the EML map is actually the embedding into that prism. Right, and prisms play a role in this TR-TC thing as well. When we take the table reduction map, we need to actually, we get a bunch of surjections. We actually need to go back into BE, and that requires applying a table completion map, which is again an embedding into surjections as a bunch of prisms in BE. So there's a very similar story of taking an EML map of an AW and taking the table completion of the table reduction. I'm saying a lot of words here, but yeah, hopefully they'll come together eventually. But yeah, there's a lot of analogies here between these maps in the Cartesian product and yeah, similar maps on the apparatic side, except instead of like AW EML, we have table reduction, table completion. Yeah. Okay. So yeah, let's just do another computation. So same computation. This was the hard way. This is the way, like, essentially we don't want to do it, and we want to replace this with our operatic calculus, which should compute the same result in the end, which is this 1, 2, 3, 2, which is essentially the only important information that we want. We don't need to keep track of all these crazy number of terms if we're just going to apply AW at the end and just get this one coaction term, right? Why write down, thousands and thousands of these terms when I can just write down this one number? So that's essentially the importance of this stuff. I want to replace like all of these giant numbers of terms and then take AW with just this one coaction. Okay, so let's do the other computation. Hopefully the board is good. Yeah. So we'd like to say it's the coaction of some surjections, but which ones? So that's where this calculus comes in, and then we just have to prove that this, calculus is essentially correct. And that's the second conjecture. Okay, so I'll call this like the operatic picture. Right, in this picture, you're applying these delta maps, Xi, and instead of AW, you have this detuppling and table reduction, table completion thing. I will appreciate if you discuss wiki page homology, because I know a little bit of algebraic topology. I don't want to interrupt you if you don't want. Yeah, let me go over this real quick, and then I'll talk about homology in a second for sure. Let me just get this out first. So the operatic picture, again, we're gonna have very similar thing. I'll label them a little bit differently so that you know that they're actually different. So this will be like delta up. This will be a delta that operates on this upgraded Barat-Eklis operad stuff. And then we have this capital H to distinguish it from the lowercase h that was acting on the Cartesian product. So this is an operator for the operatic stuff. I'll call this HTR. There's like a different H, which not important right now, but and then finally we can detuple and then apply the table reduction to whatever the BE elements are that we get from detuppling. And so what was the composition we had before? We had delta 1, 2, then we had Xi, so instead I'll just replace it with, I'll just write big H, and I don't want to write the TR every time, but so it's delta H, delta 1, 3, and then instead of AW, we'll have this detuppling TR. Right, so this was analogous to what we had before, which was delta 1, 2, or I'll write upgraded here to differentiate it. This is just regular delta 1, 2, then little h, then delta 1, 3, and then AW. So you can see how every map has its like analogous map over here. AW is analogous to this composition here. Delta 1, 3 is like this upgraded delta 1, 3. Little h is like the big H. Yeah, same thing. And so initially, we can view our simplex, instead of as a simplex in C star M, we can sort of do something which seems trivial, is we can just kind of give it like a base point, which is we can, instead of viewing sigma in C star M, we can view it in C star M tensor this upgraded BE. But I'm just going to basically tensor it with like a point. So it's going to be like just 1, like that. So there's an embedding here where I just send every simplex to simplex tensor this one object, right? So all of this stuff I'm going to be applying to this operator here. So it's sort of like the simplest BE element, right? It's a permutation of one thing, and the partition is a partition of one partition. So it's a partition that includes only one thing, and there's only one permutation. So this is basically the only element with, when the arity is 1, when you're only permuting one thing. And so what we're going to be, instead of plugging in sigma into this stuff, which is what we were doing before, right? We plugged sigma into delta 1, 2, then applied Xi homotopy, then delta 1, 3, then AW. We're gonna, instead of plugging this in, we're gonna plug this in. So it's like kind of like a shift here. Instead of looking at the simplex itself, we're just gonna do all the math on the operatic side, on this one thing. So what we're gonna do is we're gonna plug in 1 here. On the operatic side, we're going to end up with a BE element here, and then we're going to apply table reduction to that BE element. And that should give us that 1, 2, 3, 2, which was the final coaction thing. So let's do this computation real quick. Let's show that we do get, in fact, 1, 2, 3, 2, the same result that we got, theoretically that we would have gotten if we had actually proved that AW was this coaction. But yeah, so let's just start the calculation here. So when I apply delta 1, 2 on the upgraded BE, on the operatic side, I just get, maybe I should really write it like that. So it's really just 1, 2. H, 1, 3, upgraded, V table reduction. Right, so I just applied 1, 2, so 1 became 1, 2, and it's in the same partition. When I apply H to this, though, now, H acts a little bit differently on the BE side, on the operatic side. So I'm going to get a 1 simplex out of this because I'm starting with a 0 simplex, and it needs to increase degree by 1. But what I'm going to end up is with like an element of degree 1 in this upgraded operatic thing. So I'm going to end up with, so table reduction of phi of delta 1, 3, upgraded. And what I'm going to have in here is 1, 2 in the same partition. Or yeah, that was right. And then the next one, it's going to be split. So it'll be like 1, 2, and it got detupled here. And if I'm being really careful, the HTR, there would be like a table reduction, table completion composition as well, but in this case, they're both the identity when it's acting on degree 0, so it just goes 1, 2, 1, 2, and it's just itself. So that's fine. Then when I apply delta 1, 3, again, it acts very similar to what happened before. So now I just get 1, 2, 3. And then 1, 3, 2. And it's very important here that the ordering changed here. So when I apply delta 1, 3 here, I get 1, 3 together in the same partition here, but 2 is separated. And in the original one, the 1, 2, and 3 are in the same partition. And so their ordering is actually different than the ordering here, if I view them like detupled as just normal permutations. And that's what the phi is telling me to do. So now I'm just getting normal elements of BE. So the solution should be the table reduction of this BE element, which is just, 1, 2, 3, 1, 3, 2. And the table reduction you can check actually is 1. Well, if you find all the degenerate ones, it would be like 1, 1, 3, 2. That's degenerate though, and then 1, 2, 3, 2. And also 1, 2, 3, 3, but that's also degenerate. So that one's degenerate, that one's degenerate, so we just get the 1, 2, 3, 2, which is what we were looking for. I should have learned more topology. No, don't call yourself stupid. I mean, this is like very advanced stuff. But yeah, we'll go over. You want to talk about some homology stuff? So yeah, this is showing us that we can compute that same coaction term. Actually, wait. Let me say one more thing, and then I'll go into the homology stuff. So it's my thinking that actually I can just write it right here. Yeah. So it's my thinking that if you do these compositions of maps either on the operatic side or on the original picture that I was drawing before I erased everything, there should be some, I think it's just a straight up isomorphism. I don't even think it's a quasi-isomorphism, but I think there's an isomorphism between the simplices, which are like sigma, tensor, all this operatic stuff, which is the composition of these, like this map, this operatic stuff. And I believe there should be some, if you do these maps, there should be some isomorphism, I believe, of, simplicial sets, I think, between these simplices and the simplices that you get from the original picture, which are just the, delta, the non-operatic stuff. That's probably the easiest way I can just say it real quick. Stuff in the Cartesian product. So this is in, this guy is actually just in C star of M tensor with this upgraded BE stuff. So they live in two different spaces, but my theory is that essentially they're the same shape. They're the same simplices. That if you take first of all, if you take the tensor product of two chain complexes, you get another chain complex. So yeah, chain complex here. BE upgraded is also a chain complex. You take their tensor product, you get a chain complex. Hey, you're muted. Well, no one said that, so I don't think I'm muted. Am I gonna have to start banning people that say that? I think you're trying to get banned. Okay, so yeah. Basically, the story is that, and there should be a lot of structure preserved in this isomorphism, actually, in the sense that that once I take the AW at the end, that the AW of this non-operatic stuff is essentially the coaction of the table reduction of all this operatic stuff. So that's essentially what I'm trying to say. There's a very, 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 very strong relationship, and it also carries over into, like I was saying, once you take the Alexander-Whitney map, there should be some operatic relationship between taking the Alexander-Whitney map over here and taking the table reduction, the coaction of the table reduction of the operatic stuff over here. Table reduction and then coaction. I guess you could say. So yeah, it's this is the story that needs to be basically proven or spelled out completely, that there's this relationship between the sigma tensor operatic stuff that you get from this operatic picture, and then once you apply table reduction and the coaction of those surjections, it should be the same thing as applying the Alexander-Whitney map to the non-operatic stuff that we get originally from all the graph homology stuff, which lives in this Cartesian product. Okay, right, so let's go over, do you want to go over some homology and topology stuff? I think that would be pretty cool. So yeah, I can go more deeper into the research probably another time. Also, we had a little bit of incident with one of the chickens earlier, so that was not good. She actually survived, but yeah, it was almost a catastrophe. But there was like this giant eagle or something that was trying to eat her. It wasn't pretty. All right, so yeah, slight GPX2. Did you want to talk some homology, topology? We can look at the Wikipedia page. We can go over some definitions. I think that would probably be helpful to people that are watching the video as well, if they don't know. Yeah, I want to understand homology better. Okay, perfect. Yeah, let's go into. So maybe somebody will somehow get through the first 4 videos, and then they'll see some basic homology stuff, and they'll be like, oh, now this all makes more sense. But this is very on topic, so I think this goes well with the video. Yeah, let's go to Wikipedia. Yeah, we can look at Wikipedia real quick. Yeah, so these are our main things that we study, these chain complexes, right? So it's just essentially, they like to write it all fancy like this with the arrows, but it's essentially just a sequence of groups, abelian groups, or in general, they could be R modules for some ring R. Usually it's commutative, or pretty much always. And then these differential maps, that's where all the kind of the magic happens. So you can think of each n-dimensional piece as sort of being made up of, it's like a free abelian group on n-dimensional triangles. So, when n is 2, like I was saying before, you just have normal triangles. When n is 1, you just have like lines. So you can imagine even with just like lines and triangles, you could probably build a lot of different shapes by sort of connecting them together, right? Here, so let me show you something on the board real quick. So let's just see like what kind of shapes we can draw just from these. So this is called the one simplex. This is just like 0 and 1. It's just a line. Then you have like a regular triangle, which is 0, 1, 2, like that. And if you just take like just these 2 shapes, there's like a lot of different things you could build from this. For example, I could take a triangle here, and yeah, you could kind of think of it as being filled in as well. It's like 2-dimensional. I could take a triangle, and I could just take a bunch of line segments, and I could build, anything basically, right? And the inside here is not filled in, so this is like a hole. And this shape has non-trivial homology because essentially this hole creates non-trivial homology. Now, we haven't said what homology is yet, but you can think of homology as somehow measuring the holes in a space. So the holes in a space that you can build out of all of these triangles. So yeah, slight GPX. That's like the visual picture you can kind of think of. It's essentially like a study of, all the different shapes you can possibly make with these higher dimensional triangles, and also connecting them together so they can sort of share some of the boundary parts as well. But yeah, what they were writing before when they have these maps, like Cn maps to Cn minus 1, maps to Cn minus 2, etc. on the Wikipedia page. This is called the boundary map. So the boundary map tells you from an n simplex, it breaks it into the boundary pieces, and it tells them how they fit into the n minus 1 picture. So for instance, here we have this two-dimensional triangle, but it's sharing part of its boundary with this line segment is both, you could think of it as a line segment that's making up part of the boundary of this thing, or you can also think of it as a line segment that's a piece of the boundary of this. So there's actually information here in the boundary map that tells you, basically how all the space fits together. So is it connected with triangulation? Yeah. So there's a theorem that, like, if you have, I'm not sure exactly what you need, but I know for smooth manifolds it works, that for every smooth manifold there's some simplicial complex, which basically just means if I take a smooth manifold, there's always some way to build up from all these triangles. I can build the same shape up to homotopy, which just means like they're essentially the same shape. Meaning that, like, in topology, maybe you've seen this before, but a triangle and a circle are topologically equivalent to each other. So they have everything that you could possibly ask about it in terms of its topology. All the things are the same. So they have the same homology groups, same homotopy groups, etc. So yeah, like a triangle is a triangulation of a circle, which is a smooth manifold. And there's a theorem that if you take any smooth manifold, there's some non-unique, it doesn't have to be unique, but there's some way to throw a bunch of triangles together and create a shape that's homotopic to it, which just means, it's essentially the same shape. So yeah, triangulation is very important in topology. And that's just saying that for basically any compact shape, I can always just take a finite number of triangles, throw them together, and create the shape from triangles, basically. Right. And then the homology is going to be essentially you take all these groups and you take the kernel of the boundary map and you mod out by the image of the previous map. So I don't know if you've taken any group theory or anything like that, but essentially there's a definition, which is just that, you have to prove that this definition kind of makes sense or is important, but you have this differential map which lowers the degree by 1. You can think of it as a boundary map. It sends every n simplex to the boundary of the n simplex, which is 1 less degree or 1 less dimension. And then the ith homology group is going to be, maybe I just got to make sure I don't get the indexes wrong, but I think it's just the ith. It's the kernel of Ci. Maybe I might have these indices wrong, but let me think. So kernel, and then mod the image of the previous map. I think that's right. Or I'm off by 1. Or maybe it's I plus 1 and I, or I minus 1 and I. Yeah, it's either this or this is an I minus 1 and this is an I. I can't remember which one. I think this is right, though. You can check. We'll check the Wikipedia page real quick. So yeah, so you can see here they talk about. Oh, also this is important, right? If you compose two of the D's in a row, you also get 0. That's very important. That just means that every boundary. So if I take an n simplex and then I take the boundary of it, and then I take the boundary of that shape again, the boundary of a boundary is 0. The boundary, basically, you take the boundary map twice, you get 0. Then you look at all the kernels and all the images. Yeah, I had it right. And then the homology group is the Zn mod this Bn, which is the image of Dn plus 1, which is what I had. Yeah. And that's your definition of homology group. And again, this is just essentially telling you it's some sort of information about the holes in the space. If it's an abelian group, it could be a free abelian group, or if it's a module over a field, it'll be a vector space, and then you can talk about the dimension of that vector space. And you can sort of think of the dimension of that vector space as counting the number of holes, or the n-dimensional holes in the space, in some sense. But that's not a perfect analogy. But you can think of the homology groups as sort of keeping track of, in some sense, the information about the holes in the space. So you have like a circle has like one hole, but you could have like a donut in 2 dimensions, and it has a one-dimensional hole. It also has like a 2-dimensional hole. So yeah, there's all these types of things. Okay, so hopefully you liked that quick little introduction to homology. Do you have any more questions I can answer? I think that's probably like a quick 10-20 minute introduction to homology. You have these spaces you can build from these n-dimensional triangles. You have a chain complex which comes from the information in that, and then the differential map tells you about how all the boundaries of all the triangles fit together. You can define these homology groups, and these tell you about the holes in the space. Like if you have modules over a field, then you'll have vector spaces, and you can look at the dimensions of these vector spaces, and that tells you information about the holes usually. And if you're not a vector space, you get some more like fine-grained information about, like, sometimes it can tell you about information about the orientability of the manifold, or if it's non-orientable. There'll be like some torsion in the homology groups. So there's a lot of information in these groups or vector spaces depending on, what's the coefficient ring that you're working over is. But yeah, do you have any more questions about that? Hopefully you're still tuned in. Anybody else questions? Homology? So just to summarize today, we essentially went through a calculation, like a raw calculation, a difficult calculation on the like, without using any operatic stuff. We just were looking at the pure maps on the Cartesian products that involved these joins coming from the Xi homotopy, delta, and Alexander-Whitney map. And then we were talking about a way to translate everything over into the operatic side so that all we had to do was take a table reduction at the end. And the theorem that we want to prove is that the coaction of that table reduction map, which is a bunch of surjections, should be equivalent to everything that we get, or the coaction of that should be equivalent to what we end up with after we take the Alexander-Whitney map of the complicated stuff that was kind of hard to deal with. Can I explain better the HI part? What do you want to know? Oh, do you know about quotient groups? So this would be like a quotient group. You have a kernel as a subgroup. These are abelian groups. So kernel is a subgroup, image is a subgroup, and, or sorry, I mean, yeah. Kernel is a subgroup. So this is a subgroup of the quotient group, which is, CI mod the image. So yeah, in the quotient group, essentially what we're saying is that the image, everything in the image of the previous map, so this would be like delta I plus 1 or n plus 1 in this case. This is delta n. So everything in the image of this map is a boundary of an n plus 1 dimensional simplex in the complex, right? So by modding it out on the bottom, we're saying that everything that's a boundary of something in this group is now equivalent to 0. So essentially you can think of it as you can move through the boundaries of higher dimensional simplices without sort of changing the element that you're looking at. So modding out by this is just saying, okay, everything that's the boundary of an n+1 dimensional thing, that's now 0. And everything that has no boundary here, that's in the kernel of this map. So it's saying I want to know all the n-dimensional simplices which have no boundary, but also don't come from the boundary of an n+1 simplex. And that's why we take this quotient group. So yeah, I think it's probably easier to understand if you go through some simple examples, like try to take a triangle which is made up of 3 vertices and 3 edges, and try to compute by hand the homology of that. So you'll have a C1 and you'll have a C0 and you'll have a boundary map, delta 1. This map, this will just be 0 because there's no higher dimensional simplices. So this map is just the 0 map. Yeah, so you could figure out this is going to be 3-dimensional or spanned by 3 elements. This will be spanned by 3 elements. And you could actually write down everything that's going on here and actually compute these, figure out what this quotient group is, and actually compute what the homology here is. And you should get that H1, if you do homology over integers, you should just get H1 is, the quotient group will just be isomorphic to the integers. So yeah, I would say to understand homology more, just literally compute the homology of the triangle here. And if you can figure out all the definitions and stuff that goes into doing that, by the time you finish reading about all that stuff, you'll understand homology pretty well, I think. So yeah, try to compute that the first homology group of this triangle is, and we're not including the middle of the triangle. So it's just there's just a 1-dimensional piece and a 0-dimensional piece. There's 3 0-dimensional vertices and 3 1-dimensional vertices. And no 2 simplices. So yeah, that would be an interesting thing to try, interesting exercise or homework problem if you want. Yeah, any other questions? I think I can probably end around here, and then I'll have to prepare a little bit more for the next research one, because we're getting into I think I've basically sort of outlined everything that goes into the proof, but now it's just a matter of actually taking steps towards the full argument of the proof. Okay, yeah, that's good. All right, yeah, unless anyone else has any questions, I think I'll just end it here. So we talked about the joins in the Cartesian products, which are these complicated terms. We had to take the AW at the end, but it's not clear what we get. We want to prove a theorem that says it should just be the coaction of a bunch of stuff that we get from a bunch of operatic compositions. And at the end of that story, we'll get a bunch of BE elements. We take the table reduction, and then it should match up with the coaction of that table reduction. Should be the same thing that we get the AW of the hard stuff with all the crazy amount of terms that most of them end up. We get a bunch of terms on the Cartesian side, but because a lot of them include a lot of degeneracies, and we're applying the Alexander-Whitney map at the end. If any of the degeneracies show up in any of the tensor factors, they're just 0. So essentially we have a lot of superfluous terms, which once we apply AW, most of the terms are not important, essentially. And that's what we want to prove, is that, yeah, most of the terms don't matter, and the terms that do matter, those are just the coaction terms that we get from the conjecture. Okay, yeah, let me end recording here. I can stick around if any